But let me start by saying how wonderful it is to take some time out of our busy days, including my busy day, to share thoughts about the universe. And I think all of you being here means you also enjoy doing this, which is taking some of your time and getting to this wonderful place to hear a little bit about the universe. So first, I know that the questions are at the end, but I have a picture here that I want you to tell me if this was taken in the northern hemisphere or the southern hemisphere. Anybody knows? Southern. Why? Magellanic Clouds. So we found at least one astronomer in the room. Anybody else? So what he's saying is, so this is first a beautiful picture. I hope you can enjoy just the awe of we're going to see Jupiter tonight, but the awe of a place, and I hope you all had a chance to go to a place far away from New York City so that you can see a beautiful sky. So this sky is in the southern hemisphere. It is in Argentina and Patagonia, and you can see many different pieces of the sky, and the Magellanic Clouds is exactly what gives me the notion that this better be the southern hemisphere. So what he saw is these two clouds, which are actual galaxies. These are small galaxies, neighbors to our own major galaxy, which is this guy, right? So the Milky Way is also shown, but you can see the Milky Way in both hemispheres. The southern hemisphere sees the center, which is thicker, but in principle you could see the galaxy up here too, but you wouldn't see the Magellanic Clouds. And there's a comet, so if you're a comet hunter you would know the year. This is 2014, and this is a wonderful picture. And the reason I wanted to start with this image is to try to zoom together out of where we are, right? So imagine that we're not here, we're in a place, say in Patagonia, and the sky is amazing. And you have a very powerful telescope. But let's first look at our galaxy, which is sort of the obvious close. So the closest object that you can see in the sky is the comet, and probably a couple planets after that. And then there are lots of stars. And the first big galaxy is the Milky Way, and then you have the Magellanic Clouds. Now, we see a lot more galaxies than that, but let's just look at our own galaxy. And this is a map of that the same galaxy, our Milky Way. We are in it. So this is a projection of the sky. So it wraps around us, right? So we open up that sphere, which we call the sphere of the sky, and we open that up and project the whole galaxy. And you can see these two baby galaxies here are the Magellanic Clouds that were in that image. So this is the big structure of what we observe out there. You could also say, let's take a piece of the sky and just zoom in. And let's zoom in to the level of like 10, divide the moon by 10 pieces by 10 roughly, so you get a little square, say in the middle of the moon, just for scale. And you zoom it into a place that has nothing, no stars, nothing you could see with the naked eye. And if you zoom in with a powerful telescope, say the James Webb Space Telescope, you will find pictures like this, right? So you would see an area filled with galaxies. In this picture, you see a lot more than galaxies. You also see a big bright star, a couple of them. Those things that sort of look like a star you put on a Christmas tree are real stars. They just have so much light that they make these little edges. In real life, they're just a point, but they have way too much light. And then you have, I think you might have heard about this before, you have gravitationally lensed galaxies, which make this sort of banana-shaped orange things show up in very interesting forms. And that's a distortion because there's way too much mass in this cluster of galaxies in whitish, in the center here. So this is just an image of a tiny little piece of the sky with nothing special for the naked eye, but really, really powerful telescope. So James Webb is the most powerful telescope in optical going into this very bean-like structure. So what I was trying to contrast between this image and this image is the big sphere and the little tiny pieces, right? So different images of the same sky, but zooming into a little piece or seeing the whole sky. Now what you can do also is look at the whole sky in galaxies instead, and this is one such survey. It's the Sloan Digital Sky Survey, and each of these dots are galaxies. So this is the sky a piece of the sky, a 20th of the sky, with every single dot being a different galaxy. So the universe out there has a ton of galaxies. That's, you probably knew that already, but this image to me shows, wow, it's really a lot. The universe might be infinite, so there might be infinite numbers of galaxies, but observable galaxies are usually a finite amount because there's time that it takes from the galaxies to get the light to us. And you can make pictures of what's an observable part of the universe by looking deeper and deeper and seeing more and more galaxies. What has happened recently, you probably read on the news, is the start of what we call the Vera Rubin survey, let's put it that way. So it's the Vera Rubin Observatory is in Chile, and this is a survey that started this past February, and it's taking, instead of images, videos of the sky as it goes by and trying to map even higher level of knowledge of the sky. So this is now starting. It's an ongoing project, and there are many faculty at Columbia and all over the world working very intensely to have a complete map with videos. Now, the difference between an image and a video is, well, from your cell phone, you plug into different parts of your cell phone, but in reality for us is that when you do a video, you also see things that change. If you take a picture, you accumulate the light coming from an object. You could take another picture and it may change from day 1 to day 2, but with a video you can see things change in real time and you can accumulate the whole sky. So it's basically a constant scanning of the sky, and that's going to be an amazing set of data. Now, I wanted to just use a video here to imagine flying through the galaxies, through the space, to empty space. And I want you to imagine that not only you're flying through, but that these galaxies are actually flying away from each other. So when you measure galaxies, their velocities and their distance, you find the universe is expanding. I'm sure this is not news to you, so this is sort of an image of the universe expanding, kind of, it could be. And you also discover that that expansion is getting faster and faster. And the second piece, the acceleration of the universe, is a huge puzzle for us. So we don't know why the universe is accelerating. That's one big question. We also don't know what is the whole material in the universe, because dark matter is part of it. But we know it is expanding and accelerating. So imagine now that we're doing it the opposite direction. Okay, so imagine now that instead of expanding, the universe is contracting, which would be equivalent to going back in time. So what would happen if we go back in time? All the galaxies end up piling on top of each other, right? And then all of us pile on top of each other. So it's going to be pretty crowded, pretty hot, pretty dense, and not very comfortable. So, but that's the reality of the history of the universe, is that if you go back in time, everybody is on top of everybody, and it gets pretty hot and dense. Okay, so that's the past of the universe, and this is an image that tries to give you that history in one slide. So going back in time, so here's James Webb that I just mentioned, the Hubble before it, trying to go back in time. And as you go back in time, you have the galaxies sort of not quite formed yet early on, maybe the first stars, first galaxies early on, and eventually you get to be so hot that you're hotter than the center of the sun, for example, much hotter. Okay, so eventually it's so hot that there are no galaxies, and that period before it's making what we call before what's called the cosmic microwave background. Between that time and the dark age is when then light begins again. So there's a period of a lot of light, and then there's a dark age, and then eventually stars start being formed and galaxies. Okay, and then if you keep going back, you end up in the Big Bang. And how exactly the Big Bang happened, how exactly this beginning started, we don't know very well. But we know a lot of things, especially the people that work in Nevis have tried to get as close to the Big Bang as possible using a different system, which is particle physics. It's looking for the particles, looking for interactions of particles. That is one way to get the closest to the Big Bang, is to understand how when you're on top of when everybody's on top of each other, how do things move, how do things interact, and basically that density is what we can try to reproduce in accelerators on Earth. So let me invert that picture just to be able to do it in a different scale, because we're going to live on this picture for a little bit. I don't know how many of you have seen this picture before? Okay, the same that knows about the Magellan Cloud. And John, you don't need to answer, okay. So, all right, so a lot of you haven't seen it before, so I'll walk through it, okay? So this is the same idea as that one, right? So this one, I think it's pretty clear, right? So this one is looking at the universe, zooming back to some beginning. And as you look further away, you look at the past, because when you look away, the light that you're seeing left that object in the past. So as you look deeper and deeper and deeper in the universe, the more the universe is young. You see the young version of the universe. And eventually you see it so young that there are no stars, and that's the dark ages. And then you can see even before that dark ages, because there is a leftover image from the beginning of the universe, a leftover radiation that we call the cosmic microwave background, which are these background radiations which are today in the microwaves, which is the same microwaves that heat up your coffee from time to time, or your milk, or your soup. Those microwaves were generated in the beginning of the universe. They are flying through the universe, and we observe them today. And that gives us a ton of information about the beginning. But going past that cosmic microwave background, closer to the beginning, is really hard. So if we go to this image, it's the same history of the universe, but now for a particle physicist kind of view. And so what we've done with this image is basically stretched it into orders of magnitude instead of sort of more linear versions of the history of the universe. Okay, so let's walk through it. We are here with this, thinking person, the sculptor. So this is today. So today we have this background radiation at 2.7 Kelvin, which is minus 454 Fahrenheit. It doesn't matter. I think, to be more precise, minus 455 Fahrenheit. Okay, so it's cold. That's the universe today. If you go back in time, that temperature, which is here in Kelvin, it's going to get hotter and hotter. So 3,000 degrees Kelvin. Then you get to 10 to the 7, which is the core of the sun. So here is when the universe has the same temperature as the core of the sun. And then we keep going further and further. And to get to temperatures of 10 to the 15 Kelvin, which is pretty hot, we can do that in accelerators. Okay, so particle physicists, and you've probably seen this before, we have the Large Hadron Collider. Let me go there. You might have seen this image, I hope. So the Large Hadron Collider, the LHC, has protons of very high energies, and they collide in the CMS and Atlas. Ooh, that just came. Oh, there it is, Atlas. Those collisions are like if in that split second, very small amount of time, is living in this time. Okay, so this is living as if the particles, the material that you're shocking, and all the energy is living at the same time as, say, the universe was when it was 10 to the minus 10 seconds old. Okay, so you can try to understand the beginning of the universe by doing these experiments. Okay, and so I wish I could ask questions, but John told me not to. All right, so hopefully this is clear enough that humans can try to reproduce the beginning of the universe by smashing atoms together. And when we do that, not only we are reproducing the conditions of the early universe, but we're also discovering what matter and energy and all the particles and the forces of nature are made of. So by doing these experiments, what we've learned, I'm sure the table of elements became basically, electrons with a nucleus. The nucleus has a neutron and proton. They are made of quarks, and the electron is still a fundamental particle. And our new table of elements is much smaller than that big one that I never was able to memorize. So I'm much happier that I can memorize this one versus the big one. So the little one is what we think of the standard model of elementary particles, and it explains everything we see except for the dark matter, the dark energy. And gravity is not in the table either, so one more force. So in red, you have the forces of particle physics, which are the weak and the strong forces, nuclear forces, and the electromagnetic force with the light particle, photons. You have the quarks that make the protons and neutrons up and down, and then two more copies of the same type of quarks. You have the electron that generates electricity in your wires. That one is our most familiar fundamental particle. And then there are two copies of it that are heavier, the mu1 and the tau. And then we have the three neutrinos over here, which are very similar to the electron, mu, and tau, except for that they have very little mass and they have no charge. So they're similar, but they're different. They have some similar properties. They have the one same interaction, which are the weak interactions, but they don't have the electromagnetic interaction. So they do not emit light. They don't react to light like the electrons do. So the neutrinos are ghost-type particles. They go right through us. They don't interact with us very much. They're showering. There are billions of them crossing my thumb, and yours too, every second. So there's a shower of neutrinos coming right through us, and we don't interact with them at all. So those are one of the hardest particles to study because they don't show up very often, but we knew that they existed. And by playing more and more tricks on the particle physics world, we can actually know a lot about them. The last particle to join this table is the Higgs, which was one of the major efforts of the LHC, and it's an amazing achievement that was predicted and finally discovered in the Large Hadron Collider. So, Anne here wanted to know more about neutrinos, right? So neutrinos, as I mentioned, they're in this table. They are these three. They're pretty interesting in a few senses. One is that I already told you it's hard to detect them. They go right through us in this room, and they're going through us a lot. Why are they going through us? Because almost every nuclear reaction around all the stars and the sun emit neutrinos. So every time you cook things in the sun, because the sun is it's a huge nuclear furnace, it's emitting a lot of neutrinos. Nuclear reactors emit neutrinos. They go right through everything else, but we can, with very large water-type detectors, we can actually study these neutrinos. So my work is to try to study these neutrinos, but very special version of them. Now, let me give you another interesting fact about neutrinos, that there are three flavors, just like all these. So if you look at the table of quarks, the up and down make the proton and the neutron. One thing that we haven't figured out why is that there are two more copies. We call these generations. There are three generations of the same thing. So up and down, there's the charm and strange, the top and the bottom. These are copies of these, except for that they are heavier. So there's 1, 2, 3 generations, just more massive, okay? And so those heavy generations tend to decay to the lighter generations. So the everyday life on Earth is mostly up and down. And these others are only seen in very high energy interactions, which happen on the atmosphere too, but a rare event. And this is what makes this table is all done with up and down quarks and electrons. But the neutrinos, because they're so light, we actually have those three neutrinos going through a lot of the time. And one interesting feature is that if the sun, for example, only creates electron neutrinos for a while, by the time they get to us, you will have the three of them. So by moving around, they actually change flavors. So they not only are hard to detect, low mass, not much interaction, they also change from one to the other. So they transmute from one to the other. So those are some of the facts about neutrinos. And so why am I so interested in neutrinos? So the thing that makes them hard to study, which is that they don't interact, makes them really interesting to do astronomy with, right? So when we're looking at those amazing telescopes that our optical astronomy friends have built, the James Webb Telescope, the Vera Rubin Telescope, all these telescopes are looking for light. They're looking at one of these particles, this guy here, photons. Now, photons or light particles, they are, the ones coming from this beautiful light in my eyes and in all the light around you. That light can be absorbed. And so when it's flying through the universe for a very large distance, from time to time, it will be absorbed. Neutrinos go right through almost everything, so they hardly ever get to interact very much. So one of the fun things that we would like to do is to understand far away, high-energy systems that emit neutrinos and photons, but we don't see the photons. We don't see the light. We only see the neutrinos. And so that is one reason why we care a lot about it, because those neutrinos will tell us about things we cannot see otherwise. So it's worth our effort to study them. And so but the tricky part is how do we detect them, okay? Now, there are other particles that come from the space out there. So let me just show you, for example, here's a list of transient type systems out there. In the middle is 2 neutron stars colliding, which are, this is not a real detection, this is a study that is predicting what will happen. And in the final phases, there will be lots of light, but there will be neutrinos even before the light comes out. So that is one such system that we would love to catch the neutrinos from. These kinds of systems also emit gravitational waves, yet another form that we can detect that is not light. So there are different ways, we call these multi-messenger approaches to understanding the universe out there. There are other things like this. There's black holes that emit flares from black holes. We have gamma ray bursts that we're still trying to understand exactly what they are, but they could be similar types of explosions. We have binary systems that could be not only the neutron star ones, but black hole systems. So we have tidal disruption events. We have a few events out there that make the beautiful, quiet, galaxy-expanding universe look a lot more violent and much more transient. So things are moving around, and we as astrophysicists would love to understand what's driving these things. So understanding both the light that we detect and the whole spectrum of light that comes out of these events, but also the neutrinos. And one more group of particles that are very dear to me are the cosmic rays, which are also accelerated in very interesting places like shocks, from supernova explosions of stars. So the combination of trying to understand everything that reaches us from very far away makes us be driven to detect these very rare particles. The other reason for studying neutrinos and cosmic rays is the fact that we can see them at much higher energies than anything else, even higher than the LHC accelerator. So there are what called high energy cosmic rays here in this picture of getting closer to the beginning of the universe. You have high energy cosmic ray energies at these scales. So a little further than the accelerators, but this is a lot harder to study because we don't control the collisions. The collisions happen. Cosmic rays are protons, iron nuclei, all kinds of elements that are accelerated to energies which are higher than anything we can do on Earth, and they show up, and when they reach the atmosphere of the Earth, they interact with the atmosphere and they make beautiful showers of particles. So here's a image, actual artist's conception of what a shower might look like for a cosmic ray that hits our atmosphere. So here's the Earth. Here's some galaxy far away, but here's some cosmic ray that arrives at such high energies that it interacts with our atmosphere, and they make these showers. We've seen many, many of these, and these are called extensive air showers, and you can observe them with very special detectors. So my foray into this whole area starts with us building a very, very ambitious project. How many of you have been to Argentina? Oh, good. If you stopped in Brazil, that would be nice, because I'm Brazilian. She went to Brazil too. Okay, so, the first picture was in Patagonia, that's in Argentina, and the piece of the picture, and this detector that we built is also in Argentina, and Brazil is over here. I am from this area over there, Rio. But this is where we built. These are very close. This is an area close to the Andes. We built a huge array of detectors to study these highly energetic particles that we don't know where they come from. So 2 different topics, but related. One is understanding the highest energy particles that shower on our atmosphere that nobody knows the origin from, and understanding how neutrinos get generated and how to observe them. And the reason I'm bringing those 2 topics is because the same type of detectors can see both. But since neutrinos are rare and hard to detect, we see many more cosmic rays than we see neutrinos. And so we're still hunting for the neutrinos with these types of arrays, but they should be detectable at some point in the future. Here, what you see is a artist's conception of one of these showers that I mentioned before. So it's one tiny little say, proton, so a hydrogen atom nucleus, so a tiny, tiny, tiny thing that has so much energy that it generates billions and billions of particles. Those particles, throughout the atmosphere, they hit the ground and they can cover, in terms of an emission of radiation, a circle of many, 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 many miles. Okay, so each of these yellow dots is a different detector of particles. I'll show you what they look like in the next slide. And they are separated by about a mile, 1.5 kilometers each. Okay, so the fact that it can make a signal in this huge area means that there's a lot of energy in this tiny little subatomic particle. These are really impressive, just amazing what nature can do. And the things that are, so the yellow, so here's say a proton or hydrogen nucleus hits the upper atmosphere with tons of energy. The type of energy I showed you before in the other slide, they make the shower, they hit the ground, the shower particles, not the original, the daughters particles hit the ground, make this huge imprint on the detectors on the ground, and then they also have these other emission. The shower itself emits ultraviolet light that we can see from far away. So we built 4 telescopes that can also look at this light directly. So we see the same shower with 4 telescopes and with these detectors on the ground. We built this array in Argentina, in Mendoza. If you were interested in the Malbec wine, you would stop at Mendoza area and have a little bit of Malbec, my suggestion, but don't drive after that, sleep, and then the next day you drive a few hours down to Malargüe where our observatory is. And this was a very long build project called the Pierre Rouge Observatory. 19 countries participated, and it was led from Chicago where I was before, and we built these 4 telescopes and 1,665 tanks, which I'm going to show you, which are these dots throughout this whole space. So here is a younger version of me with one of these detectors. So this was when we started the project in, this is around 2000 and a few, so 20 some years ago. This was an engineering array, and then the final product looks more like this. And here's a picture of the actual deployment. So the distance between these two is 1.5 kilometers, 1.5 kilometers, 1.5 kilometers. So this is one of those lines of this huge array covering 3,000 square kilometers of area to see these amazing events coming down. Okay, so these are simple detectors. They are a tank with water in it and photomultiplier tubes. They are self-powered by solar panels, so we don't plug them into any grid. Here's the detector, and then there is a GPS antenna for time. We don't need to know where they are. They usually sit where they are, except for cows moving them around, but they like to scratch their backs on the battery box. And then, basically the reason we use GPSs is to say what time it is, not where you are, because we know where they're supposed to be. And then we have a radio signal communication antenna that gives to the central campus all these different data from all the different detectors. So that's the layout of the ground array. And then you have these 4 telescopes, which are not the kind of telescopes that takes images in the optical. These are ultraviolet telescopes that look at this very fast moving. So what they're looking for is that ray that was presented here. But the ray is basically a light bulb, a faint ultraviolet light bulb moving at the speed of light. Okay, so it has to be very fast cameras. CCDs don't do it. We need to use photomultiplier tubes for this kind of cameras because they collect the light quickly. They can process electronically quickly. Because CCDs on our cell phones, they usually accumulate light over time, and this moves too fast for that accumulation. So that's the technology that we developed for this amazing project. And now I'm going to move into, oops, if I can find my thing, there we go, into what happened after that. So we built this array. We got amazing data, but we didn't finish answering the question. We didn't actually get the answer for where are they coming from. And what happened is that 3,000 square kilometers is not enough. And when you think of 30,000, 100,000, 300,000 square, that's like countries, right? And to enlarge this a factor of 10 or 100 to get the answer, it got a little bit difficult to implement, although there is a group of people, group of countries trying to think that through. There is an effort in China, there's another effort in Europe trying to, not to actually deploy in Europe because that's too much space for Europe, trying to coordinate large efforts in Chile or in Argentina. With China, things got complicated, geopolitics got involved. But so there will be yet another level of scale in this kind of effort. But I thought we needed an alternative approach. We couldn't just keep enlarging these tanks throughout much larger areas because these are actually farmers' lands and we need to coordinate with them if they're okay putting these things down. And it takes a huge amount of interaction and many outreach lectures to make sure that everybody is okay, that these things don't radiate, they're not dangerous or anything, they're just sitting there. So we are thinking what to do in the ground array region in terms of the future, but what I thought we would do is plan for a space mission. And the reason to go to space is because what we're actually doing is observing the atmosphere of the Earth above this array. So if we could put the same telescopes that we built, but smaller versions of them, up in the sky, we could see a much bigger, wider volume of our atmosphere. So we could use one telescope above instead of many, many detectors on the ground. So we designed that. This is the Poema over here. We got money from NASA to design this mission. And we designed a very nice mission with 2 telescopes that look down on Earth, and they can see these showers of these very high energy particles. And they can do 2 things. They can see the downgoing cosmic ray ultra high energy particles coming down that flash this ultraviolet light, and they can see upward going showers from neutrinos. So let me show you what that crazy idea is. So here, suppose you have 2 neutron stars or 2 black holes far away in one direction, emitting all these neutrinos. They will go, say that you're sitting somewhere here in my telescope, either in space or with a balloon telescope. This neutrinos will come through the Earth, and they will generate what's called a tau lepton, and they will make a shower just like these downward going cosmic rays. So it's upward going instead. So it's as if a particle crossed the whole Earth and showered upwards, which cannot be the nucleus of protons or hydrogen or any of the normal elements, because those don't go through the Earth, right? So it needs to be a ghostly particle that goes through the Earth and make the shower upwards instead of downwards. So by looking at the atmosphere as a whole, with the Poema telescope, for example, you can see both the showers that are coming down, which are the normal cosmic rays, or the ones coming from the ground, which would only be able to be neutrinos. Okay, so that's our trick to look for these very difficult to detect neutrinos. We look for upward going showers instead of downwards. So we do both. So that's the design that we made. And we got wonderful, very happy to get the design money from NASA. And we also calculated the price tag, which is a bit high. And we also discovered that there are many technology issues that we need to resolve. So what we started doing, so this design was in 2019, but we had started already a little bit earlier by flying balloons and making a small version of the same kind of telescopes and taking it to the space station. So one of our projects here, called Mini Yuzo, is currently on the space station in the Russian part of the space station. This was built before the Ukraine invasion, so in case you were wondering. And it is sitting there, and it's being used, astronauts or cosmonauts use that telescope to look for these showers coming down from the space station. So that's one piece that we built early enough. In 2019, it was already deployed. And it's been really helpful to us, but it's not seeing a ton of these events because it's too small compared to the kind of numbers of events that we want. Then we have, since 2014, been doing balloons. So that we did one test balloon in 2014, then SPB-1. So this is, now let me introduce you to some acronyms here. You know, if you work with NASA, you have to come up with acronyms. There's no other way. So my favorite is Poema, which in Portuguese is poem. But the cool thing, if you're going to make acronyms, don't make it poem, because then you Google poem and you get lots of poems. And poema with one M, you would get lots of Brazilian poemas, or Spanish too. So with two M's, you only get a few hits. I think there's one software company and us, so it's very cool. So that's and what it stands for is Probe of Extreme Multi-Messenger Astrophysics. Okay, so we found a way to make a good acronym. The other one, which I don't like, I didn't make that one. I inherited it from a collaboration with the Japanese and the Europeans called EUSO. It started as European-US Observatory, and then anyway, it's a long story, but it became, the same acronym became Extreme Universe Space Observatory, and we've used the EUSO acronym for a few balloon flights. Mini-EUSO is the one in the space station, and then SPB-1 and SPB-2 were the two flights, the most recent one in 2023, that we flew with NASA flights. SPB stands for super pressure balloon. Okay, so super pressure balloon are special balloons that NASA has that are super pressurized. And the idea of these balloons is that they float on the atmosphere, and they can go on for 100 days going in circles around the Earth. And so I'll show you more about those. So this is what we're trying to build, and the next thing we're doing right now at Columbia and in a few other institutions, a collaboration of about 60 people compared to the thousands in the Auger Observatory. We're building this telescope that will be flying in 2028 with also one of these super pressure balloons, and I'll tell you a little bit more about it. But let me just show you, you've already seen the mini-EUSO in the International Space Station since 2019. Here is the team getting ready for SPB-2. So here is some of our postdocs, graduate students, and my co-PI for this balloon payload. And what we did was we built two telescopes, one to look down for these neutrinos coming up, and another to look, one to look down for the cosmic rays going down, and another to look towards the limb of the Earth and below to be able to see the cosmic rays and the neutrinos, so to do both things with the same type of telescope. And here's the launch vehicle before launch, hang tests, not the launch vehicle, but the hang tests, and everybody getting ready. And we are in a beautiful place, I also recommend, and that is New Zealand. And the idea is to go to New Zealand, which is over here. Let me actually find a better place to show you the same thing. To launch from New Zealand, where NASA has a launching place instead of if you heard about balloons before, you're likely to have heard about them in Antarctica, which is another great place that NASA has to launch balloons. We rather be a little bit higher in latitude, closer to the equator, opposite of the number, but anyway, closer to the equator, because we want dark nights. If you're in Antarctica, you don't have much of a night while we're flying. So here's a better area for us. And we launched from New Zealand, and with the winds, which here's what winds can look like, very stable, rotating around the Antarctic continent, we can, in principle, in 4 days, be over Chile and Argentina and come around and around. That's the idea. NASA has had many flights so far, but the one in 2023, there were two payloads, us and Superbit. Superbit went before us, and they went around and around and around for 27 days, and they had a really nice flight. We had a leaking balloon right away, so our beautiful flight lasted a day and a half, which was not what we wanted, but we got enough data from there. Here's the actual launch, which is the scary part when you've been for years building a beautiful telescope and off it goes, and it looks pretty clunky. I'll show you a video later. And you're like, oh, are they going to drop our baby? They eventually did, but a day and a half later. All right. Now, what is in these kinds of balloons? So what we're building are these cameras that try to see, remember I was saying these showers are a light bulb, an ultraviolet light bulb moving at the speed of light. So it has to be very fast cameras. And the kinds of cameras that we build are two types. One with these photomultiplier tubes, but instead of big ones, tiny little ones. They're multi-anode, this is very technical, but for those who care about these things, they're pretty cool. And that we take pictures every microsecond, which means that we take 1 million pictures per second. Okay, so that's a lot of pictures. And then we have an even faster camera, which is on the other side with silicon PMs, and that one takes 10 nanosecond pictures, so that means it's 100 million pictures per second. So that's a lot of pictures. These are simple pictures. They're not full of contrast. They are trying to find a light signal moving. That's all it's trying to do. And the challenge is technology is first taking these pictures is pretty tough, and then downloading data and powering these cameras are pretty difficult. So that's why we're doing balloons, because before we go to space, we have to show that we can deliver. And showing that this works very well on balloons is what we're doing. And we actually do some science while we're developing the technology. And so here is what we're building now, which is this Poema. We call it, let me go back so that, no, I'll go forward. Let's go this way. So we call it Poema Balloon. Poema is the space mission, but now on a balloon. So it's a version for a balloon, a smaller version with radio, because friends of ours who are experts on radio detection of neutrinos decided to fly with us, and then we have these coordinated signals of both the Cherenkov emission and optical, ultraviolet also emissions, and radio. So we get a lot of different signals from the same events, which are these showers of particles coming through. Okay, so that's what we're building now. The idea is, again, to fly in 2028. We will have these downward-going ultra-high energy cosmic rays showering in the atmosphere, emitting light towards our telescope. We're going to search for tau neutrinos coming from interesting events in the universe, and we're also going to see cosmic rays that come horizontally at us. So those are some of the science that we'll be doing, and that's really exciting. I think we're looking forward to doing so. And as we study these things, what we're trying to do is both understand these amazing, those amazing objects that I talked to you about, so understanding the astrophysics of the most energetic events in the universe. At the same time, we're trying to understand what interactions, how the particles and neutrinos and quarks and all these other interesting particles interact at energies that we cannot reach with our own accelerators. So I think this is a good place to start slowing down. So I'm going to just show you a video of our launch and answer some questions. So here is...
Okay, guys, release the balloon. Release the balloon.
They're saying, release the balloon. There it goes. So these balloons have the size of a football field once they are completely inflated. The helium in them, it doesn't look like a full football field yet because it's not all inflated, but as it goes up, it inflates further and further. And this is our dangerous time. As there is a parachute below the balloon. So the idea is that if you end up in a place that is amenable for us to land, the parachute brings us down calmly. If you're in the middle of the ocean, it doesn't matter if you have a parachute or not, because you're going to go down all the way down. So this is our launch in a beautiful area of Wanaka, New Zealand, and I highly recommend a visit there too. And the launch was beautiful, but unfortunately it had this little problem. All right, so let me just stop here and answer some questions. I don't know if I can. Yep, that's good. Okay, thank you so much.